Welcome back to BrainOmega. This is PyTorch tutorial number 6. Today we're stepping into the world of image classification with the CIFAR10 dataset, one of the most popular benchmarks in computer vision. In this tutorial, we're going to build a complete image classification workflow step by step. We'll start by creating a data pipeline with PyTorch, setting up datasets, applying transforms, building data loaders, and adding some augmentation to make the model more robust. Then, we'll add device-agnostic training utilities so our code runs seamlessly on GPU if available, or CPU otherwise. From there, we'll walk through 4 different models, each one a little more powerful than the last. Model A, a simple linear baseline, just a flattened layer followed by a linear classifier. Model B, a multi-layer perceptron with nonlinear activations. Model C, a small CNN, our first real computer vision network. Model D, transfer learning with torchvision.models.resnet18, a modern pre-trained backbone. Along the way, we'll track metrics and visualizations like accuracy and confusion matrices so we can really see how the models are performing. We'll also learn how to save and load the best model so your hard work isn't lost when training finishes. And finally, we'll put our model to the test, making predictions on random test images and even on your own uploaded images. By the end, you'll have a practical, end-to-end template for image classification in PyTorch that you can reuse, extend, and apply to real projects. We'll start by importing the core libraries for this project. From PyTorch, we bring in Torch and the neural network module NN. From Torch Vision, we import datasets and transforms. These give us easy access to common image datasets and the standard pre-processing steps they need. We'll also use PyTorch's DataLoader to batch and shuffle data efficiently. Finally, we import matplotlib for quick visualizations so we can actually see sample images and predictions as we go. Right after the imports, we print out the versions of PyTorch, Torch Vision, and matplotlib. This is a small step that saves headaches later. If something behaves differently on another machine, you can quickly compare versions. We also print whether CUDA is available. That tells us if there's a compatible NVIDIA GPU we can use for faster training. Last, we set a device variable. If CUDA is available, we'll use CUDA. Otherwise, we'll fall back to CPU. Keeping this in one place makes the rest of the code device-agnostic. Whenever we create tensors or move a model, we'll send them to device, and the same script will run smoothly on both GPU and CPU. With libraries loaded, versions confirmed, and the device selected, we're ready to start building the image pipeline. We'll kick things off by making our experiments reproducible. The setSeed function fixes the random seeds for Python, NumPy, and PyTorch, both CPU and CUDA, so when you or someone else reruns this notebook, you'll get the same results. Same data shuffles, same weight initialization, same outcomes. That's essential for debugging and for fair comparisons between model variants. Next, we add 2 tiny utilities that make training easier to track. Print train time takes a start and end timestamp and prints a neat summary of how long training took on the active device, CPU or GPU. Use it around your training loop to see the speed difference between devices or settings. An accuracy fan is a quick, no-frills accuracy helper. It compares predicted labels to the true labels and returns a percentage. It's perfect for simple sanity checks, even if you later use Torch metrics for richer reporting. With seeds set and helpers ready, we've laid the groundwork for repeatable experiments and clean, readable logs as we build out the rest of the pipeline. CIFAR10 is a classic vision dataset, 60,000 color images, each 32 by 32 with 3 channels, spread across 10 everyday classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. we'll prepare it the right way for training and testing. First, we define the per-channel mean and standard deviation commonly used for CIFAR 10. These values let us normalize images so that each color channel has roughly 0 mean and unit variance, which usually helps models train faster and more stably. Next, we build 2 transform pipelines. For training, we include light augmentation, a random horizontal flip, and a random crop with 4 pixels of padding. These simple tweaks make the model more robust by showing it slightly varied versions of the same image. We then call totensor, which converts PIL images to PyTorch tensors and scales pixel values to 0, 1, and finish with normalize using the CIFAR 10 stats. For testing, we skip augmentation. We want a fair, stable benchmark, and apply only totensor and the same normalization. With transforms set, we create the train and test datasets via datasets.cifar10, pointing to a data folder, enabling download equals true, so the files are fetched if needed, and attaching the appropriate transform pipeline to each split. We also grab class names for easy labeling during visualization and evaluation. In the next step, we'll wrap these datasets in DataLoaders so we can batch, shuffle, and stream them efficiently to the model. Before we start training, it helps to see what the data looks like. Because our dataset is normalized for the model, colors would appear off if we plotted tensors directly. So we create an inverse normalization transform, ENV norm, that undoes the per channel mean, ST we applied earlier. Right before plotting, we pass each image through ENV norm and then clamp values to 0, 1 so the display looks natural. The showBatch helper picks a random set of images from the dataset using torch.randperm, arranges them in a small grid, and renders each one with its class name as the title. PyTorch images are stored as channels first, C times H times W, but Matplotlib expects height-width channels, so we transpose the tensor to HWC before calling imshao. We also turn axes off for a cleaner look and use tight layout so the grid fits nicely on screen. Calling show batch train data n equals 16 gives you a quick gallery of unnormalized training samples, perfect for checking that your transforms are working as expected and getting a feel for the variety inside CIFAR10 before you build the model. Now we'll wrap the datasets in DataLoaders, which handle batching, shuffling, and background loading for us. We set a batch size of 128, a good starting point for CIFAR 10 on modern GPUs. For the training loader, we turn on shuffle equals true, so each epoch sees the data in a new order. This usually helps optimization. For the test loader, we keep shuffle equals false, so evaluation is deterministic. We also set numWorkers equals 2, which spawns a couple of background worker processes to preload batches while the GPU is training the current one. This helps keep the pipeline fed. And pin memory equals true speeds up host to GPU transfers when you're using CUDA. The last line prints how many iterations per epoch you'll get for train and test given this batch size. With these loaders, you've got an efficient, device-friendly data pipeline that keeps training smooth and fast. To keep our notebook clean and reusable, we'll wrap the core training logic into a few small functions. The first one, train one epoch, runs a single pass over the training set. We put the model in training mode. This makes layers like dropout and batch norm behave correctly, then loop over the data loader. For each batch, we move images and labels to the chosen device, GPU if available, otherwise CPU, run a forward pass to get logits, compute the loss, and do the standard optimizer steps, 0 grads, with set to none equals true for a small speed/memory win, backprop, and step. We also track running totals so we can report the average loss and accuracy across the whole epoch. Accuracy is computed by taking the argmax over class scores and comparing to the true labels. Next is evaluate, which is the same idea but for the test/validation split. We decorate it with torch.nograd and switch the model to eval mode so PyTorch skips gradient bookkeeping and layers act in inference mode. This makes evaluation faster and more consistent. We again accumulate loss and accuracy across all test batches and return the averages. Finally, fit ties everything together into a simple training loop that runs for a configurable number of epochs. It sends the model to the correct device, initializes a history dict to store loss/accuracy curves, and times the entire run so we can print a neat summary at the end. Each epoch we call train 1 epoch and then evaluate, append the results to history, and print a friendly line with the latest train/test loss and accuracy. When it's done, we call print train time to show how long training took on this device and return both the history and the duration. With these helpers in place, the rest of the tutorial can focus on models and data, while training stays compact, readable, and device-agnostic. We'll start with a super fast baseline. Take each 32 by 32 by 3 image, flatten it into a single vector of 3072 numbers, and feed it straight into a linear layer that outputs 10 logits, 1 score per CIFAR 10 class. That's exactly what linear baseline does. NN flatten converts the image to a 1D feature vector, and NN linear 3072 to 10 learns a simple weighted sum for each class. There's no convolution and no hidden layers here, so don't expect high accuracy. The goal is a quick sanity check that our pipeline, data, transforms, loaders, and loops is wired correctly. We fix the random seed for reproducibility, move the model to the active device, GPU if available, and use cross-entropy loss, NN cross-entropy loss, which takes raw logits and integer labels. For optimization, we choose SGD with a learning rate of 0.1, a straightforward choice that works fine for this tiny model and keeps the training dynamics easy to see. Finally, we call our reusable fit function for 5 epochs, which trains on the loader, evaluates on the test set each epoch, prints loss and accuracy, and returns a history of metrics along with the total training time. This linear run establishes a baseline we can beat when we add nonlinearities and convolution next. Now let's add capacity with a small multilayer perceptron. Instead of sending pixels straight to the classifier, we first flatten the image and pass it through 2 hidden layers with ReLU activations. Those ReLUs give the network the nonlinearity it needs to model more complex patterns than a single linear layer ever could. In this setup, each hidden layer has 256 units, a sensible starting point for CIFAR 10 when you're not using convolutions. The final layer still outputs 10 logits, 1 per class, and we'll keep using cross-entropy loss so we can feed in raw logits directly. For optimization, we switch to SGD with momentum and Nesterov enabled. Momentum helps the updates carry velocity in promising directions and damps out noisy gradients, which usually speeds up convergence. We keep the learning rate at 0.1 to start. Paired with momentum 0.9, this often trains faster and more stably than plain SGD. We seed for reproducibility, move the model to the active device, and run our reusable fit loop for 10 epochs so the MLP has time to improve over the linear baseline. What should you expect? Typically, the MLP will outperform the flatten-only model because those hidden layers can combine pixels in nonlinear ways. It's still not as data efficient as a CNN, which exploits image structure, but it's a great demonstration. Simply adding ReLUs and depth lets the network learn curved decision boundaries in pixel space and push accuracy beyond the linear baseline. If learning seems unstable, try lowering the LR to 0.05. If it plateaus early, try training longer or increasing the hidden size to 512. Now we'll switch to a convolutional neural network, which is designed specifically for images. Unlike MLPs that flatten pixels and ignore spatial structure, a CNN looks at local patterns, edges, corners, textures, and builds them up into higher-level features. Our small CNN has 3 feature blocks. The first block uses 2 3x3 convolutions with 32 filters each. Padding keeps the size the same, followed by a max pool that halves the spatial size from 32 by 32 to 16 times 16. The second block repeats the idea with 64 filters, then pools to 8 by 8. The third block uses 128 filters and pools to 4 by 4. This progressive downsampling means the network learns more abstract features while keeping computation reasonable. After the feature extractor, we have a small classifier head. Flatten a linear layer to 256 units with ReLU and a final linear layer to 10 logits, 1 per CIFAR 10 class. Because we're producing raw logits, we keep using cross-entropy loss, no softmax needed in the model. We seed for reproducibility, move the model to the active device, and train with Atom at a learning rate of 1 times 10 to the power of -3 for 10 epochs using our reusable fit loop. What should you expect? This compact CNN should clearly outperform the linear and MLP baselines because it exploits the 2D structure of images and shares weights across space, making it both data efficient and parameter efficient. If you want a little extra accuracy, try light augmentation, already in our pipeline, train a bit longer, or add batch norm after convolutions. If training is slow or memory is tight, reduce channels, for example 16 to 32 to 64, or batch size. This model gives you a solid, practical baseline for 32 by 32 images. Now let's level up with transfer learning. Instead of training everything from scratch, we'll take a pre-trained ResNet 18, a model that's already learned rich visual features from millions of images, and fine-tune it for CIFAR 10. We load ResNet 18 with default pre-trained weights, then swap out the final fully connected layer so it outputs 10 logits, 1 per CIFAR 10 class. Everything else stays the same, which means we get powerful feature extractors, edges, textures, shapes, right out of the box. ResNet 18 expects 224 by 224 inputs, but CIFAR 10 images are 32 times 32. To keep things simple, we wrap the model with a tiny resize wrapper that upsamples each batch on the fly using bilinear interpolation before passing it through ResNet. That way, we don't have to rebuild our data loaders or transforms. The wrapper handles sizing transparently. For optimization, we use Atom W with a small learning rate, 0.0001, and weight decay, 0.0001. Small steps are key in transfer learning. You want to gently adjust the pre-trained features to your new task rather than overwrite them. We fine-tune all layers here, nothing is frozen, which often works well on CIFAR 10. If you're short on compute, you could freeze the backbone and train only the final layer as a quick start. Finally, we call our fit loop for 5 epochs to get a strong baseline fast. What to expect? Even with minimal tuning, a pre-trained ResNet 18 typically beats small scratch models by a healthy margin, thanks to its general-purpose features and deeper architecture. If you want a bit more performance, train longer, use a short warm-up on the learning rate, or unfreeze gradually, start with the head, then the last block, and so on. This gives you a practical, reusable template for transfer learning on new image datasets. Let's wrap everything up by comparing models side by side. We collect 2 simple numbers for each run, the final test accuracy, the last value from the history, and the total training time in seconds. We put those into a small pandas data frame so we can display a neat table and sort it by accuracy to see which model came out on top. This makes it easy to spot trade-offs. Maybe one model trains much faster, while another gets a few extra points of accuracy. Below the table, we draw a bar chart of test accuracy. Each bar represents one model: the linear baseline, the MLP, the small CNN, and the transfer-learned RESNet 18. It's a quick visual that tells the story at a glance. You should see the MLP beat the linear model, the CNN beat the MLP, and the ResNet 18 transfer model, typically leading the pack thanks to its pre-trained features. A couple of quick notes for fairness. We trained different models for different numbers of epochs and with different optimizers, so this is a practical comparison, not a controlled benchmark. If you want a strict A/B test, equalize epochs, tune learning rates, or run multiple seeds and average the results. Still, this table plus chart combo is perfect for summarizing what you built and for deciding which model you'd like to refine next. Now that we've trained several models, let's see where the best one still gets confused. First, we pick the winner by sorting our results table by test accuracy and grabbing the top entry. We map that name back to the actual model object, move it to the active device, and switch to evaluation mode so layers behave consistently during inference. To build a confusion matrix, we run the best model over the entire test set with gradients turned off. For each batch, we compute logits, take the argmax to get the predicted class for each image, and collect both the predictions and the true labels. After the loop, we concatenate everything into two big tensors, all predictions and all targets. We use torch metrics to compute the multi-class confusion matrix. This gives us a 10 by 10 grid, one row and column per CFAR 10 class. Each cell row equals true class, column equals predicted class, counts how many images of a given true class were predicted as each class. Ideally, you want strong numbers along the diagonal. That means most images are being classified correctly, and smaller numbers off the diagonal, which represent misclassifications. Finally, we plot that matrix with matplotlib. The x-axis shows predicted classes, the y-axis shows true classes, and the color intensity indicates how many examples fell into each cell. This visualization quickly tells you the story. Maybe cats and dogs get mixed up, or airplanes sometimes look like ships at low resolution. Use these patterns to guide improvements, add targeted augmentation, tweak the model capacity, or collect more examples for the confusing categories. Once you've got a strong model, the next step is to save it so you can reuse it later without retraining. We create a saved models folder, making sure it exists, build a file name based on the best model's name, and call torch.save bestmodel.stateDict path. Saving the state dict is the standard PyTorch practice. It stores just the learned weights and biases, making files smaller and more portable than saving the full Python object. To reload, you need to recreate the same architecture and then load the weights into it. That's what the recreate function does. Given a model name, it constructs the matching network, linear baseline, MLP, CNN, or the ResNet 18 wrapper for transfer learning. For the ResNet path, we rebuild the backbone without pre-trained weights, replace the final layer to output 10 classes, and wrap with the same resize module so the input size matches. With an empty model in hand, we call load state dict on the file we saved using map location device so it loads on CPU or GPU as needed, switch to eval mode, and we're ready to use it. As a quick sanity check, we run evaluate on the test loader and print the accuracy. If it matches the number you saw before saving, within tiny rounding differences, you've confirmed the save and restore cycle works. From here, you can ship the model, resume training, or run it to make predictions in another script or environment. No retraining required. Let's see how the best model performs on actual test images. The predict and plot helper picks a handful of random samples from the test set, runs them through the model, and shows the images with their predicted and true class names. A few details make this smooth and fast. We decorate the function with torch.nograd, so PyTorch skips gradient tracking during inference. This saves memory and speeds things up. For each chosen index, we grab the image label pair, add a batch dimension with unsqueeze 0, and move it to the active device before calling the model. We take the argmax over the logits to get the predicted class ID. Since our dataset images are normalized for training, we invert that transform for display. Env norm x.clamp01 brings colors back to a natural range, and permute 120 switches from channels first to h times w times c so matplotlib can plot it. On the figure, each tile shows the prediction on the first line and the ground truth on the second. If the prediction is correct, we keep the title black. If it's wrong, we color it red so mistakes pop out visually. Call predict and plot best model test data n equals 9 to get a quick 3x3 gallery. It's a great way to sanity check what the model gets right, what it struggles with, and whether certain classes, like cat versus dog, are easy to confuse. You can bump n higher for a bigger grid, or rerun the cell to see a fresh random sample each time. If you're running in Google Colab, you can try the model on your own photos. This cell opens a small file picker. Choose one or more .jpg or .png images, and we'll run them through the same pre-processing the model expects. We load each file with PIL, convert it to RGB, and resize to 32 by 32 so it matches CIFAR10's input size. Then we apply totensor to turn it into a PyTorch tensor and normalize with the standard CIFAR10 mean and STD values, just like we did for the training set. For inference, we wrap everything in torch.nograd to keep it fast and memory light, add a batch dimension with unsqueeze 0, and move the tensor to the active device. We pass it through best_model, take the argmax over the logits to get a class ID, and display the original image with the predicted label as the title. It's a quick way to sanity check how the network behaves on real-world pictures that weren't part of the dataset. A couple of tips. Since we resize to 32 by 32, images with unusual aspect ratios can look squished. If that bugs you, consider a center crop or letterboxing step before resizing. Also remember, the model only knows CIFAR10's 10 classes. If you upload something outside that set, it will still pick the closest CIFAR class it can. If you're not in Colab, the code will print a friendly message explaining that uploads aren't available in this environment and show the underlying error. That's it for PyTorch Tutorial Part 6. Let's quickly recap what you practiced and where you can go from here. On the skills side, you learned how to load and augment image data with Torch Vision, and how to write clean device-agnostic training loops that work on CPU or GPU. You built and compared a range of models, starting with a linear baseline, then an MLP with ReLU, then a small CNN, and finally transfer learning with a pre-trained ResNet 18. You measured performance with accuracy, dug deeper with a confusion matrix, and saw how to save and reload the best model so you don't lose progress. And finally, you made predictions on both random test images and even your own uploads. But this is just the beginning. To push further, you can try stronger augmentations like color jitter or random erasing, add learning rate schedulers and early stopping, or explore other backbones like EfficientNet or MobileNet for better accuracy and speed trade-offs. You can also track metrics more professionally with TensorBoard or weights and biases, or export the trained model to TorchScript so it's ready for deployment. And if you want to really challenge yourself, here are some exercises. Swap out optimizers, use AtomW everywhere and compare results. Experiment with schedulers like cosine annealing LR or one-cycle LR. Train with mixed precision to measure speedups. Create a confusion pairs gallery showing images the model confuses most often. Fine-tune more layers of ResNet 18 by unfreezing deeper blocks and compare. Each of these pushes your PyTorch skills to the next level. So keep experimenting, keep measuring, and most importantly,